Okay, so let's get started with FreeRtos. Okay, so what is FreeRtos? FreeRtos stands for the Free Real-Time Operating System. Okay, so when we're talking about an operating system, right, what we're actually talking about is something that's running in the background. Now, if you think about something like a Linux machine or a Windows machine, there's certain processes that are happening behind the scenes, right, that are essentially monitoring and kicking off tasks for each individual application. So you can have multiple applications up on your screen, and you've got something in the background called a scheduler. And the scheduler is going to say, all right, now you can run, and then it's go to the next step, and then say, you can run, and it's going to go to the next step, and say, you can run. So even if you've only got one CPU or one core, you can still run multiple applications. Or if you've got a dual core, you can still run more than 2 applications. And the way that this happens is because you've got something called a scheduler that goes and basically says, you run, you run, you run, you run, goes back to the beginning. Now, interestingly enough, if you recall the old sort of Windows ME, remember those? Okay, so they had a problem with their scheduler, and if one application crashed, your entire system had to get rebooted. And that was partly because there was a problem with the operating system. Right, so in order for an operating system to be robust, it needs to be able to cater and handle various different things and various different tasks and so on. Okay, so this is what we're actually talking about. When we're talking about a FreeRtos, we're talking about not a whole, okay, I'm going to launch applications and I'm going to have a user interface and a GUI and what have you on a microcontroller. What we're talking about is we're talking about a mechanism to schedule various different tasks. Okay, and just something that's very important. Okay, FreeRtos is part of the ESP IDF. Now, the Arduino libraries and the Arduino framework for the ESP32 is built on top of the IDF. So everything that I show you tonight, even though I'm going to be utilizing the IDF because it's something that I like and I prefer, all right, everything that I show you tonight is also applicable in the ESP32 Arduino cores as well. So you can use all this stuff in Arduino as well. Okay. All right. So let's just have a quick look at some stuff over here. Okay. If I go through to Google, all right, and I go through to FreeRtos, I hit this website, freertos.org, okay, and as you can see, and the guy admittedly, the guy that actually created this thing, he admitted that it's written for engineers and not for marketers. It's not a pretty site. It's goddamn ugly, but it does give you some really interesting information. Now, if you go through to books and materials, and then you can download, sorry, let's get rid of all of these fantastic alerts. If you go ahead and download, right, Mastering the FreeRtos Real-Time Operating System, you wind up with this very large, very intimidating PDF that's only 400 pages long. Okay? Pizza? Pizza? Yes, please come in. Okay. So shall we take yeah, we'll just take a 5-minute. Come through.
Let's take a 5-minute break.
We'll take a 5-minute break. Okay. All right, so you download this book. Now, what I would recommend is first thing you do is you basically skip over all of the beginning of the stuff, right, until you get to the point where it's essentially talking about tasks. This is how I picked it up, because I started looking at it from the beginning and I couldn't make heads or tails of it. And then when I actually went through to the task side, then all of a sudden it started to make a lot of sense. Okay, so here we are, task functions, so I could probably do, there we are. Chapter 3, Task Management. And you start reading this stuff and it's sort of like, okay, I'm starting to get it. And then all of a sudden you download the zip file that comes along with it. And then they get some demo code going. And then it's like, oh yeah, no, it's easy. Okay, I get it. It's like, okay, that's cool. I got it. So this took me a couple of hours to get through, okay? The book looks very intimidating and it's very large. But when you actually look at it, there's a lot of pictures, there's a lot of code snippets which you read through very, very quickly. So if you're really interested in learning all the ins and outs of FreeRtos or understanding all the ins and outs of RTOS, highly recommend going through that code. It really is very good. So, right, so before we continue with some theory, I actually just want to go through a little bit of a practical exercise. Hello.
Hello.
Come, grab some pizza. Help yourself and make yourself at home.
Cheers.
So I have a client. Okay, my client comes to me and says to me, "Please create for me an application." What I really want is I want a blinking LED, and he meant that in the nicest sense of the word, blinking LED. Okay, so I do something like this, and I'm sure everybody has seen something like this, right? So I've got a setup loop, and then I've got a loop. Now this looks very sort of Arduino-ish,
yeah.
except for it's not quite Arduino code. But I'm just sort of written it over here to give you sort of an idea. Okay, so I've got a setup loop, and then I come down here. All right, now, and then I loop through, and I say set my levels to an output, or set my levels to 1, then turn it off, and then turn it on, and this is what it looks like over here on my board. You can see I've got a blinking LED. Yay, very easy. Okay, great. Okay, and I show this to the client, and he says, "That's great, thank you very much. But actually, what I really want is I want 2 LEDs. Okay? I want 2 LEDs. And you think to yourself, all right, I can do 2 LEDs. Let's see, how am I going to do 2 LEDs? All right, so I'll just basically come in here. All right, so this is what I'm going to do. All right? Because what he wants is he wants 2 LEDs, but he wants to be able to, have them at different times. So that's getting tricky. Right. So what we'll do is we'll basically have LED 1 on for 500 milliseconds, LED 2 on for 500 milliseconds, then we'll switch off LED 1 and LED 2 in that sequence. So let's go ahead and try this out. All right. So let's make sure I save it, otherwise it won't work. Okay. All right. So let's. 22, yep, I do. Thank you. Let's try that now. Okay, so, the client has come up to us and he says to me, all right, a little bit more complicated, please. Okay, now we want 2 LEDs flashing and we want them at different times. So now, what's going to happen is we're going to flash that. And bingo, we've got 2 LEDs flashing. Yay, okay, cool. That's great. And then everybody's clapping and it's very cool, right? And the client looks at us and says, no, that's not what I meant. My second LED needs to flash at 100 milliseconds, or my first LED needs to flash at 200 milliseconds. And I'm thinking to myself, now if you try and actually work that out in terms of having this event loop in here, okay, it becomes, my brain starts to hurt. And then after that, they come up to you and they say, I want 4 LEDs, and I want them all at different times. Okay? Just think about that for a second, because essentially we've got these delays in here. Okay, so every single time we delay, nothing else works. Everything has to wait. So now if I want to have something at 100 milliseconds and something else at 300 milliseconds, I've got to basically blink this one 300 milliseconds, then blink the other one, and it becomes a matter of trying to stagnate. Now, yes, there are things like interrupts that will help me, basically timing interrupts. But even interrupts, right, there's an issue with this. It doesn't scale. That's the problem. The more complex my code gets, the more requirements my code has, it does not scale. Okay? So, FreeRtos to the rescue. Let's have a look and see what actually we can do with something like FreeRtos. I'm going to actually write this out at risk of making a complete idiot of myself, okay, because I actually like to code. And I actually just want to show you what this actually looks like. Okay, so over here I've got this app main event loop, which is what we kind of set up, and then we did this loop, this while loop. What I'm going to do is I'm going to get rid of that, and I'm going to create a task instead. So let's create 2 functions. Okay, so the first one is going to be task 1. Okay, and in order for it to be a valid task, we should actually pass it a void parameter. Params, okay, and it should return nothing. It should return void. Okay, so that's task 1. Sorry? Params, yeah, there we go. And what I'm going to do here I'm going to just go back to this previous code over here. I'm just going to grab this over here. And I'm going to push that in there. So now task 1 is responsible for handling one LED. Okay. And I'm going to delete this over here. Now the first rule, okay, so first rule about FreeRtos tasks, they return nothing. You pass in a void pointer params. The second rule, and very, very important rule, is they never ever return. You've got to block them from returning. One of the simplest ways to basically stop them from returning is to just put them into an infinite loop. By the way, this code and the recordings will be shared, so you don't have to try and remember it all. Okay, so now I've got this in an infinite loop. Okay, right now let's go ahead and create this task. Right, to create the task, the first thing I need to do is make sure that I've got the FreeRtos libraries included, and this is also going to be applicable for the Arduino. Okay, and now I'm going to start with the first command called xtask create. Okay, now as you can see, the xtask create takes a couple of parameters. The first parameter is going to be the function that we've actually just created. So this is going to be task 1. The second parameter, right, is just a name. We can call that whatever we want. The third parameter, right, is how much space do I actually want to give this particular task? How much memory do I want to give it? Okay, so at this point in time, I'm just going to give it 1024 times, let's say, 2. The next one is parameters. Now over here, we can pass in a parameter, but we'll actually discuss that a bit later about what that is. And that's going to come through over here if we need it. I'm going to pass in null for now. All right, and then essentially we've got this other concept called a priority. All right, and priorities we will also discuss in detail in a little bit, but essentially that depends on how, which task. If it's got a choice between two tasks, it's going to pick the higher priority. Okay, and then the last one is a task handler, which I'm not going to need right now. We'll go have a look at that a bit later as well. I'm going to make that null as well. Okay, so now that I've actually done that, okay, actually I do need to set up as well. So let's just go ahead and make sure that we've actually set up our LED. Okay, let's try and actually compile this and see what actually happens.
Excuse me, I'm coming late, but what C interpreter is that?
Sorry?
What C interpreter is that?
What's C interpreter? It's a compiler. It's compiled.
Oh, compiler.
Yeah.
Well,
Oh, it's just GCC. It's part of the IDF. It's part of the sort of suite of frameworks that you get for the ESP32.
oh, right, the standard one.
Yeah. All right. So what actually happened with regards to that is I've now got my blinking LED back. Okay, fantastic. Good. All right, thank you. But now check this out, right? So this is actually running on its own task. So what I can do here is I can essentially just copy this. Let's make this, let's say, 200 milliseconds. We'll make this responsible for number 2. And we'll call this task 2. And then over here we can just basically create another task. And this will be task 2, and that's all good. Okay. Now, let's run this. Yeah. 1 second. And what we wind up with is 2 individual applications running at the same time. Okay, that's the point. So they're essentially 2 idempotent, totally independent threads. They work on the same CPU, they work on the same thread, but they're actually, as far as it's concerned, they're autonomous. Okay, So this is one of the benefits of the FreeRtos. It gives us the capability of writing, instead of one massive application, we try to interleave timings and stuff like that. It gives us the capability of basically splitting up our applications, complex applications or complex tasks, into simplified little versions of applications. So over here you could say I've got two tasks or two little applications that are running independently. Okay. So
you just said on the same thread.
Yes.
So they can't bump into each other. They're literally interleaved.
That's right.
Yeah.
Yeah, that's correct. All right. So I'm just going to show you a couple of things within here. So firstly, right, what we actually have is we've got, at this point in time, right, in that application, we actually at one point had 3 tasks. Okay. The first one is actually at main. So when it starts off, when it actually starts behind the scenes, it actually creates a task. That task then goes ahead and creates 2 other tasks. We can then go ahead and decide how much memory we want to actually give each one of those tasks. It'll take memory off the heap and apply it to those particular tasks, which they can then use individually for their own stacks. Okay? Is everybody okay with the concept of heaps and stacks? Does anybody need some explanation on that? You all good? You'd like some help with that? Yeah. No problem at all. Okay. So in computer terms, right, specifically with RAM, we've got this concept of a heap. It's just huge amounts of space that we have, right? It's just memory. Okay. Now every single time we actually call a function, we declare local variables. Right? We take those variables and we put those on the stack. Okay, so essentially, let's say for example, we start off over here at 0. Okay, we call our first function and it has, let's say for example, a couple of different, it declares a couple of different integers and some char arrays. Then we basically use that much stack. Now what will actually happen is also that function might call another function, which has some additional memory, right? And now it goes to some others. So what we wind up with a bunch of different memory over here. And the reason why it's called a stack and not a queue is because a stack basically works like a bunch of plates. If I take some plates out of my dishwasher, I put them down, and then I put some more on top of that, and I put some more on top of that, and I wind up with a stack of plates. Now if I want to clear those plates, I don't go from the bottom. There would be a queue. A queue basically is someone lining at the back. So a queue is like somebody at the bank. The first person who comes in is the first person that's served. A stack, the first person who, the last person who came in is the first person that gets served. So I take stuff off the stack. So what will happen is when I'm actually running that function, it'll eventually exit out of that function. Now all of those pieces of memory that were inside that function are out of scope. Nobody cares about them anymore. That disappears off the stack and I get that space back. And then the next function runs and then that disappears off the stack. Okay? So the heap, when we basically do something that there's a C programming, a C function called malloc, memory allocation, right? What that basically does is it takes memory off the heap and basically allows me to use that, right? So essentially we've got this thing of heap. We can create memory or we can create variables within our heap, but we can also basically use local variables and that'll basically fill up our stack. And one of the problems that you will run into with things like the Arduino is that if you basically have functions with bigger and bigger program memory, or if you put them into recursive loops, you eventually get a crash, and it's called a stack overflow. It means that you've actually utilized more memory than you had available on the heap, and then your stack just runs out of space, and that causes a crash. Okay, does that clear it up? Yeah. Cool. All right, so that's essentially what we do with the FreeRtos tasks. So coming back over here, just to quickly show you, we can see that we allocated some memory. Each one of those then run independently, and I'm allowed to use that much memory within that particular task. Okay. All right. So now the next couple of little things are quite interesting. I'll just show you what they look like. So the next one is the tick scheduler. Please have a seat if you would like to. Just welcome, grab yourself some pizzas, make yourself at home. Okay. This is kind of like what is actually going on here. Okay. So we've got 2 tasks. Okay, and we've got something in the background. that is monitoring those tasks. Okay, it's called a scheduler. And it's going to basically say, to look at task 1, it's going to say, all right, you run for some time. And then we're going to hit something called vtask delay, which is a delay. And the minute it does that, right, the program stops. And then what will happen is the scheduler will say, okay, well, something else can run now. Let's go to task 2. And task 2 will run for a while, it'll hit delay, we'll go back to task 1. And so on and so forth, okay? So that's how that works. So we've got the scheduler who's basically monitoring how these things actually work. And here you can actually see the kernel runs in tick interrupts. So essentially there's an interrupt happening on the various different ticks. Okay, so we run task 1, interrupt kicks in, says which one am I going to run now? Selects one, runs that one, then the interrupt kicks in, and then the scheduler basically decides again which one it's going to run. So that's how that works.
Does the interrupt work as a switch or?
No, it's just a timer loop inside the actual FreeRtos. Now there is another task which is a little bit invisible, but it'll become apparent over here, and that's the idle task. The idle task is essentially not doing very much. Most of the time your chip doesn't do very much, unless it's doing some very heavy computation or spinning in some sort of for loop or something like that. It's usually just waiting for something to happen. So we can see that we run a little bit of task 1, a little bit of task 2, and then it's sitting there idle. And these are our delays. This is when we're waiting for stuff to happen. Okay, and that's essentially what we call the idle task. And that's actually a task that we could. It's a task that we could actually do certain things with if we want to. On some of the other more modern chips, they actually, when it gets to idle tasks, they just basically automatically go to sleep. We don't do that on the, as far as I'm aware. But you know, just to be aware that it's there. And now we've come through to the last little one that I wanted to show you, which is task priority, which is interesting because we talked about this concept over here that we've got this this over here. Now we can basically say 3 over here. That'll make this one a higher priority. Okay, 0 being the lowest priority, the higher the number, the higher the priority. And what's interesting is that the scheduler, right, while it's running a task, right, it will run a task and then essentially say, okay, I need to basically decide which task to run. What it will actually do is it'll basically figure out that if there is a higher task priority, even though the other task is in the middle of something, it will basically run that task, right, and until it basically gets to a blocking point for the delay or something else, and then it will run the previous task that it was running. So over here we can see that it was running that task, the high priority took precedence, it then finished, it then drops back down to the lowest priority, and then after that back to the idle task. So behind the scenes, it's basically sort of doing all this stacking in terms of, so it'll run a couple of CPU cycles on here, a couple of CPU cycles in there, back to the first one, and so on and so forth. And the good news is we don't really need to worry about that. We can just think of these things as individual applications within our program. Okay, so, right, so that was sort of an introduction to tasks. Now, what is interesting is that, you know, from a programming perspective, I look at this and I think to myself, I don't like this idea that I've got 2 tasks that look identical. Why not do something like this? Yeah. Right, let's have a look and see what's happening here. Oh, no, that wasn't it. Did I not save it? I've overridden it. Alright, so I'll just show you what we can do over here very quickly. Right, so we've got, I'm going to take this one out. I'm still going to have 2 tasks, but this time what I'm going to do is I'm going to call I'm going to call the same method, right? But let's go ahead and create, what we can do here is we can actually just pass in some parameters that'll allow us to decide how we actually want to run these things. So let's see. Let's create a I had this preset up, but I've kind of seemed to have overwritten it. I'm sorry about that. So let's go ahead and do this, right? Type. If it becomes too arduous and painful, I'll skip it, but let's just see if I can get it right. So I'll do a type def struct. And what we'll do over here is we'll basically just call this thing something like led params. And we'll basically have in there two things that are of interest. First one is going to be an int, and it'll be the LED. And let's call it lowercase LED. And the second one is going to be an int, and that'll be time. Okay, int. Okay, so what we'll do here is we'll create a structure. LED params, we'll call it LED params. Sorry.
Live coding.
Live coding is always fun and always susceptible to the most severe screw-ups. Okay, so what I'll do over here is I'll just say that the first one is going to be LED is going to be equal to LED1, and the second one, which is going to be time, is equal to let's say 1000. Okay, and this is LED params 1.
Just realized that's a C syntax.
Yeah.
Not available in C++.
Oh yeah.
Yeah.
Okay. Well, you can always just create them and just add them manually.
Around.
Yeah. And then I'll just basically make that 2. So what we'll do here is we'll basically say that we're going to pass in ampersand LED1, and we'll pass in here ampersand LED2. Now, and then I'm just going to do this, and I'll explain to you why I'm doing this. I'm just going to make an in for loop over here, and then I'll just put in a delay. I know live coding is almost so much fun to watch, and apologize for that. So what I'll do here is I'll just basically point in void pointer params. Okay, and let's go ahead and say LED, or let's just call it LED params, the actual structure. Let's call it L is equal to the casting of LED params, and that's going to be params. And then what we can do over here, that's going to be a void pointer. Great, so now we've got L going to I made a mistake, Tim. What have I done wrong? It's a pointer. L going to LED, L going to time, and this is the last time I'll be live coding, so alright, so going back to main, Control A, Control V, and if I haven't totally botched that, we should get the same output, but this time what you'll actually notice is that we actually are only using one method. Okay, so you have the opportunity over here to actually really consolidate or make your work more precise, and to minimize sort of your restrictions. And okay, that would actually help as well if I change this. I'm just noticing that there's no change on my output, and that's because I didn't actually change it. So yeah, so you got an opportunity to, okay, so that should work now. Now the question that you might be wondering is, why did I actually put in this infinite loop at the bottom over here? It's quite simple, right? And the reason for that is because when we actually drop out there, the first thing it does is actually delete the task, and then I'm not going to get it in memory. And we can see that this is actually now running on one single application or one single function, and we're just passing in various different parameters to it. So we can actually use the same function and actually create multiple tasks, as many as we want with different parameters. Okay.
Just go through like why you put that infinite loop.
Huh? Oh yeah. So so what actually happens is, remember that this is the start at main. Okay. When it drops out of here, all right, it actually deletes the task. So it can go ahead and spawn up other tasks, but the primary task or the first task, it's no longer needed or wanted. It's essentially disappears. So the problem is that if there is a delay or anything else like that, then essentially, if I create these things over here, then of course they're going to get removed from the stack if if the task gets deleted.
So if we create a finite loop at the end, that will lead to
The original task doesn't actually have an answer. There is other ways to do this. I could have actually used malloc and actually made them as a pointer and put them on the stack. Then I wouldn't have had to actually retain this particular function.
Doesn't it infinite loop take up extra CPU cycles?
No, it doesn't. Because if you have a look at it, right, it's basically using something called vtask delay. Vtask delay is a special delay function from FreeRtos, and basically what that does is it basically says for this period of time just go and idle. So it actually just uses the idle task. Yeah. So it doesn't actually, it's not a for loop or anything else like that. So this actually doesn't cost anything.
It's a yield function,
Yeah,
so it lets other functions, other tasks take up the processing cycles.
Okay. So yeah, so that's essentially an introduction to tasks. Okay. There's one other thing I'd like to discuss with tasks, which is a little bit interesting. Okay. And then we'll basically just do a sort of a brief on that. So one of the things that we have with tasks is we've got this concept. So there's tasks. Here's the next one. Tasks, pin to call. So what this does, this is essentially the same as what we had before, but what you'll notice is that we actually have an additional parameter at the end. All right? And what this is actually telling me is that I can actually run it on the CPU that I want to actually target. So this is enabling me to do multi-threaded on my two CPUs on the FreeRtos. So you can do this with the Arduino as well. All right, so just to give you a sort of an overview, a very quick one of a perspective as to why you'd want to actually use something like this. This is enabling you to use the second core, which can be helpful if your first core is tied up doing very, very heavy duty calculations or doing something that is very, very processor intensive. Okay, but you do need to be a little bit aware about the idea that there is a reason why we actually usually only use one core for replication, and the reason for that is because the IDF, or essentially the ESP32, usually uses the second core to do things like network connectivity and wireless connections and communications and stuff like that. So for wireless and Bluetooth, whatever. This was a problem that they had back on the ESP8266. If you were connected to a wireless and you all of a sudden had to do some very heavy processing, right, you would sort of get in the way or basically stop the communications and the ping signals from happening with the wireless, and it would drop the connection. We don't have that problem on the ESP32 because it happens on a different core. So obviously if you use the second core for both, for processing intensive, you might run into something like that again. Yes?
Is it worth noting that the upcoming ESP32S1 has a single core?
That's right.
So is there some opportunity as a method where you can find out the number of processors so you can have your code all work even on one or two processor machines?
There is actually, yes. There are method calls you can actually call into the IDF that will tell you how many cores you've got. Okay. The new ESP32 has got one advantage, is that it actually comes with it comes with a USB stack as well. So you can actually create USB peripherals and stuff like that. When we plug in our ESP32 into a USB, it's got this other little chip over here. I'll just take this off over here. You've got this little chip, this little sort of square one, and sometimes it's a little sort of rectangle one. That's actually a USB to serial converter. So you don't really get USB going straight through to the chip. It's just serial communication. The new ESP32 has got direct USB. It's only got a single core. So yeah, you could basically do some interesting sort of HID, human interface devices, stuff like that. Yeah. Yeah, probably. I haven't really played with it, but that's what I would assume. Yeah, exactly.
So if something is very, you can send tasks where it only interrupts for a virtual time, you can put that onto the Wi-Fi core.
Yeah.
To get a bit of extra.
Yeah, it's also if you're not connected to the Wi-Fi and you're not needing it at that time, but you do need heavy sort of maybe process imaging or doing some sort of, maybe you're running some sort of scanning to try and actually do some AI against, let's say, an image or something like that. Yeah. Then yes, the second core could come in handy in terms of being able to do that sort of processing. You could,
So if you don't pin something to a core and you just create 2 tasks,
they'll use the first core. Yeah, by default they'll use the app core. Yeah.
and they'll stay on that core?
Pretty much. Yeah. So the only people, if unless you explicitly tell it to actually use the second core.
So you don't, if you have 10 tasks or something, they wouldn't have 5 or 1 core, 5.
No, unless you explicitly tell it to. Right. The only place that they explicitly tell it to out of the box is when they're doing Wi-Fi, internet communications, Bluetooth communications, all that stuff that needs to happen in the background where we don't want the application to crash the comms or those interrupts and so on. Yeah. Okay. Cool. So that's how we can make double the power of it. All right. So now the rest of this particular talk is actually. We've come to this interesting paradigm where we now know that we can actually create these individual sort of, you could call them applications. They're not really applications, but we've got, these tasks, and we can create as many as we want. But we've got a fair amount of memory to play with, so as long as we don't run out of memory, we can create all these tasks. Okay. The problem that then one would basically see is that these tasks have got different memory allocations. Okay. They kind of, they're kind of sort of individual. How do we basically get one task to talk to another one? And that's sometimes needed. Okay, maybe we've got a task that's sitting there, reading our I2C bus, looking at some sort of temperature sensor, and then we've got another task over here that's doing all their interconnection with, it's connecting to the wireless and connecting to MQTT broker or whatever. And all of a sudden we get this little thing saying, hey, I've got a reading. I need to basically publish it on my MQTT broker. All right. How do I get that information from that task over into this completely separate task? Everything else that we discuss over here is going to be about intercommunications between tasks.
Global variables.
Global variables, go global variables. Yes.
Put everything outside.
Don't listen to him. Okay. All right, so what is going to happen now is I'm going to really scare you because when we start looking at these things, we come into sort of, scientific or so I say, computer science terminology, which sounds awfully scary until you actually get it defined. You realize it's not really that scary. Okay, but this is essentially a bit of a decision tree, and this is the way I think. This is not officially documented anywhere. This is just my thoughts on the idea. Okay. So essentially, I want to communicate directly to another task. All right. I care about counting or sending simple data. Right. For that, I'm going to be utilizing called a task notification. We'll look at that last. Okay. Next one. Someone needs to block or unblock a task. I don't care who. In other words, I've got this other thing that's running, and I want to basically trigger and say, you can now run. For that, I need something called a semaphore. Okay. A semaphore sounds like an awfully complicated word. Right, until you actually look it up. Let's have a look at it. And it basically says it's a system of sending messages by holding the arms of 2 flags or poles in certain positions. Have you ever seen anything like this? Yeah, where people basically are communicating with flags? It's a semaphore. So all you're doing is you're taking one task and you're basically waving a flag in another task. Okay, so that's essentially a semaphore. Sounds complicated, but it's just basically a flag system saying, yeah, you can go now. Okay. The next one is called a mutex, and this is only the task that blocks another task can unblock it. In other words, I've got a precious resource. Okay, I've got a precious resource. When you're talking about mutexes, oh, by the way, mutex, mutual exclusion. In other words, nobody else can touch it. It belongs to me, mutually exclusive. Okay. So with a mutex, right, I've got a precious resource. Let's say an I2C bus. Okay, I've got lots of different things happening on my I2C bus. Lots of different people. But when I grab that I2C bus, nobody else is allowed to touch it. That's when I would use something like a mutex. I basically grab the I2C bus, I do my work, and then I release it. I step back. In the ESP32, I2C bus is not really a really great sort of example because of the way that they've done the I2C bus. It's actually really good because what actually happens is you build up all the communications at once and you send them through at one time and it comes back and that's it. It's not like you're sitting there on the bus, but if you were, then that would. But maybe serial, you could use it.
If you're bit banging something.
Yes.
Like those RGB LEDs.
Yeah, if you're bit banging something, bit banging basically means you're turning off ones and zeros to try and do communication. You don't want anybody else talking to that pin.
Because you screw up the timing.
That's right.
Yeah.
Okay. All right, now next one. I need to pass data from one task to another. For that, I'm going to use something called a queue. A queue is different to a stack. A queue basically... the first one comes in is the first one that gets out. Okay, next one. Multiple things need to happen before I unblock a task. In other words, maybe I need to read from the humidity sensor, and I need to read from the temperature, and I need some other condition to occur, and then I will basically send my information through to the wireless. For that I will use an event. Okay, so let's have a look at what these things look like in the real world. So we'll start off with a binary semaphore, or a semaphore. I'll just close this. All right. So here we can see, so we can look at this and we can immediately, by its definition, we can see that this is a task. Why is it a task? Can anybody tell me why it's a task?
Void params.
Yes, it basically passes in void params. And what else?
Returns void.
Returns void and?
Infinite loop.
And an infinite loop. Good. Going down to the bottom, we can see that we've got two tasks over here. Okay. Task 1 and task 2. All right, so let's have a look and see how this works. So the first thing that's going to happen is do something with HTTP, right? That goes off to task 1, all right? And you got this concept called X semaphore take. Actually, let me start from the beginning. Right from the beginning, we create this thing called a binary semaphore. We declare it.
Global variable.
Well, just for this file. It's not external. Okay. We create this thing called a binary semaphore. Okay. So this is just something that we create. All right. Now, that's not assigned to anything. In order for us to actually create that, right, we'll say binary semaphore, X semaphore, create binary. So we've created this binary semaphore. Now we've got this thing available. Then we'll start task 1. Notice that it doesn't actually know anything when we create it. We don't pass any of the semaphores through or anything else like that. We don't pass it through here or anything. And then we'll start task 2. All right. So task 1, right, what that does is it basically does something called X semaphore take. Now, what X semaphore take does, right, X semaphore take basically sees, is my semaphore available? Right. Now, in order for me to be able to see if that semaphore is available, somebody else would have to have given it. So this semaphore is basically a give and a take, and that's really all it is, and it's a binary. So it's either given or it's taken, and that's it. It'll either be in one of those two states. Now, I have never given it. So essentially what's going to happen is that the processor will stop at this point in time. The FreeRtos task will actually just kill the app, will stop that task from running. It's not going to proceed past that line. Okay? And specifically because I also over here said max port delay. Okay? And we'll have a look at why this is interesting in a moment. Okay? And then what will actually happen is the task, this listening for HTTP, this task over here, will start at the same time. Okay? And it's going to then print something out, received HTTP message. So I'm just sort of mocking up that I'm receiving an HTTP message, okay? And then what's going to happen is it's going to give that semaphore. See that binary semaphore? That's the same one that we're using all along. It gives that. Now, the minute it gives it, this one has an opportunity to say, yeah, I got it, I'll take it, and then it'll basically print doing something from HTTP. Then once it's done that, we'll then basically proceed with preceding HTTP message. So let's see if that is going to be as we expected. I'm just going to have to start up a new console over here, open a terminal. You notice how fast this is?
How fast?
Watch. It's actually flashing right now.
Oh, okay. No, because you really built the modules. Yeah, I'm doing the same thing right now. Yeah.
Okay, so we can, you see some messages coming through. All right, then it'll delay 5 seconds and it'll continue. So let's have a look and see what actually happened here. So the first thing that actually happened was it says received HTTP message. So remember, it started both of these, and then essentially it printed that out. All right, then what actually happened is it says doing something with HTTP, because it gave that semaphore and then it was able to print that out. And then it basically says process HTTP message, so it went back here. So the sequence of events in terms of the way that this program flow worked was 1, 2, 3. Okay? But there is something that is quite interesting. And if you have a look at these over here, they're both the same priority. Right? Let's make this one over here, this listen for HTTP, a higher priority. Okay? So listen for HTTP, let's make that a priority of 2. Now let's run it again.
Can you show me what header files is used?
Oh, it's just the FreeRtos. You actually don't even need this one.
Send. Oh, we don't need it?
No.
Okay.
Okay. So now we can see that our output is slightly different. Let's have a look and see what actually happened here. So received HTTP message, then processed HTTP message. It finished this loop and then doing something with HTTP. So the priority makes a big difference in terms of the sequence of how your program runs. Okay, the higher priority will take precedence if it's got a choice. So when it basically came to that point where it says, all right, I'm either going to continue running this current application, or I've got the semaphore which basically has been released and I can actually operate on that, the OS will make the decision based on which one has the highest priority. Okay? So that is something that you need to be aware of, and you can control your program flow like this. Now, there is something else which is quite interesting, is that we've got this thing called port max delay. Okay? And at this point in time, what that basically means is that this thing is going to wait indefinitely. Right? There is, however, something we can do with this. Let's have a look and see if we can do something like this. We can say if it was able to work, right? And that'll be within a specific period of time. So if I basically say, I'm only going to wait for 2 seconds, right? Now notice that this thing over here is waiting for 5 seconds when it gets to the end of that loop. So we'll see what actually happens. All right, I'll say else, and we'll just printf timeout. Okay. So the first thing that happened is it worked okay. Everything is okay. And then all of a sudden it timed out. And now it's continuing to time out. Then let's have a look and see why that worked out that way. So it came in here. All right, it was going to wait, and then at the same time it came in here, that processed, that fired, that fired. That's all good. Everything's fine. Then that fired. And now this is waiting for 5 seconds. This looped around and said, I'm only allowed to wait for 2 seconds. And after 2 seconds, it failed. So we can basically put some interesting sort of timers. If we've got some time-critical applications, this is how we can basically control that. And this is how we can say if something happened within a particular period of time or not. Okay. Is this too deep, or are you guys tracking with me, or is it all good?
So far, so good.
So far, so good. Okay.
I think we need the header file because when I remove the header file, it says that the tick semaphore and the GIF doesn't show up. It's undefined.
Yeah.
Yeah.
I don't think so. I think it's.
Okay. The IntelliSense doesn't work. So.
You're right.
There you go.
Okay, cool. Yeah. So you need
The
that.
IntelliSense is a bit slow, so.
Yeah. Okay.
Sometimes.
So you do need that that header. All right. Cool. So that's a semaphore. Any questions on a semaphore? No? It's not very difficult, is it?
You can have multiple symbols, right?
Yeah, you can have as many as you want. Okay. But they're just flags. They don't actually. One of the things is they're just flags. They just basically say, yeah, you can go, or I couldn't get it. You know, like something else. I was expecting somebody else to release it, so somebody else to give it. I couldn't take it, or yeah, I took it, and then I was able to execute.
One message.
Yeah, that's pretty much all they're there for. That's everything that you can do with them. All right, moving on. Next one is a mutex. So a mutex basically holds precious resource. I'm just going to go ahead and run this over here. All right, let's have a look in the code flow. So again, right, notice that the only difference between this code and the previous one is the fact that, you see, you've got the semaphore handler, mutex bus, and that could be sort of anything. And then we've also got these things called xsemaphore take, xsemaphore give. There's no difference. The only difference over here is this is not called, if you have a look at the previous code, we said xsemaphore create binary. Now we're basically saying xsemaphore create mutex. That's the only difference. Okay, so you can actually take a binary semaphore and use it in place of a mutex. Okay, but mutexes are better for handling precious resources or locking resources down. Okay, they just work better internally. Okay, I'm not entirely sure of all the nuances involved, but they definitely do work better. So if we have a look at this particular application, we've got two tasks. Task one over here. Okay, and what this does is it says reading temperature. So, and then it's essentially going to take that semaphore. It's going to wait for that semaphore. Okay, so I'm now going to take it. I'm going to basically lock it. And then what's going to happen is it's going to write to the bus. Now this is the bus over here. So this is my precious resource. Nobody else can actually, while this is happening, nobody else can actually do anything with it. Okay, and then if it doesn't work within that particular period of time, it's also going to bomb out. Okay, at the same time, we can then say reading humidity, and then we can take it, and then we can write to the bus. Okay, and this is where we can give it back. So let's go ahead and try this. Well, it's actually running it as we speak. I'm just going to stop it and just start it again so we can see it from the beginning.
The function name is xsemaphore give and take.
Yes. Yeah. So we can see that it's doing what we expect it to do. You know, it's reading from the humidity, and then essentially it's just flipping and flopping between those two tasks. And the only differences between this and the previous one is that one of those things will basically control the write to bus at a time. Okay, so nobody else is allowed to touch that because it's coming after the take. Okay, so yeah, that's pretty much all there is to a mutex. They're pretty simple. Next one. This over here is one of the more interesting ones. This is essentially direct task notifications. Now, with the other ones, I'm just going to close all of these down. Okay, just collapse that. collapse that. I'm just cleaning up a little bit. All right. All right, so with the other ones, right, we've always created a semaphore. We've always created a mutex, all right? Here, we're going to be doing something quite a bit different. Okay, notice that over here, we don't actually have any of these other intermediary objects, but we do have this thing called a task handler, okay? And where does that come in play? Well, remember that last parameter? This is where we can actually have that last parameter. This task handler, by the way, is, we can do a lot with this task handler. If we want to, for example, increase the memory of a task, we can use the task handler. If we want to delete a task, we use the task handler. So if we want to control the task, right, and we want to get a reference to that task, we can create the task handler. And that's essentially what I'm doing over here. Okay, so so we create this task. I'll just collapse this inward a little bit and I'll just show you how this looks. So we've got two tasks over here. Okay, the one is called receiver and a sender. Now, what's going to happen is the receiver over here has this uint, which is an unassigned integer, okay, and it basically is going to wait on an xtask notify wait, okay, and over here we're going to say x notify, and what we basically pass into an xtask notify is the receiver handler, the thing that we've created over here. And then we can pass in some sort of integer, a binary, and we'll come to that in a moment. And then we've got some sort of flags that we actually want to actually utilize. Okay. I'm just wondering if I actually am starting off with the simplest example. I'm not. Sorry. We'll start that again. It's a bit too high gradient. We'll start that from the beginning. Right. Task handler. Okay. Same thing. We basically have this task handler as we put it and we create it as part of the task. Now we've got this thing called a sender, which you can see is a little bit simpler. X notify give, okay, and we pass in that receive handler. So this is really simple. We just basically say go ahead and fire, and then over here we've got this thing called ul task notify take, and that's basically going to then tell us that the thing has been taken. Now watch what actually happens when we run this. So check this out. Sorry, watch this. Okay, now I'm calling it multiple times. So now it makes a difference.
So it restarts the count every time?
Well, watch what happens. So you can see 4, 3, 2, 1. Okay, so what actually happened is that it basically put all of these, it called all these notifications, right? But it didn't actually fire any of them until it basically got to this vtask delay.
Ah, okay.
And then it basically went and actually called each one of those.
So it needs to yield.
Yeah. But there's an interesting thing. So essentially what happens, so if you can, just to go over that again, right? So essentially the application went and ran that, and then came to the vtask delay and said, all right, now I can basically run another task. It went down to here, and it said, all right, 4, 3, 2, 1, go. So it actually basically did it 4 times. But now if we change this to true, we get an interesting little change. Now watch what happens with when that flag is set to true. Now it just says, I received it 4 times. Just once. So that might be helpful. I'm not sure if it's really that helpful in debouncing, but it can do. If you've got something that's very, 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 very fast and you only want to fire once, and this thing gets called multiple times, this is one way to basically throttle it.
Mm-hmm.
Okay.
Interesting.
Is this creating a queue internally?
No, it's not.
Notification?
It's just basically counting how many times it was called before it was actually able to fire it. So, you know, I basically called it 4 times or 5 times or whatever, 4 times, and it's basically just said, all right, I was able to call it, and then, okay, I can run another task now. Oh, you called me 4 times. And, yeah. Yeah. And the previous one, when we had it to true, it said fire, 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 fire. 4, 3, 2, 1. It decremented it each time.
It's almost like a normal semaphore.
Yeah, it is.
Yeah.
And you can use these in place of a semaphore and a mutex as well. All right. Now, notice that over here we've got this thing called xNotifyGive. Okay. And this is just basically returning the count, and all we basically pass to it is the actual handler itself. It's one of the more simpler versions of the xtask notifications. Right, now we've got one other one, which is a little bit more complicated, but pretty much, very much more powerful. Let's have a look at this guy. Okay, so we've got the same story over here. This time I'm not actually counting what actually happened with the output. Okay, but I notice over here I've got this port max delay, so it's essentially going to block the task and wait for the notification to occur. And then after it's actually received it, it's going to go ahead and say, I received it. Okay. Now, over here, right, I have a couple of different options that I can pass in. So xNotify is different to xNotifyGive. Give, basically, I just pass in the task handler. Over here, I need to pass in the task handler. And then I can pass in a value of some sort. And we'll discuss that in greater detail. And then there is this sort of enumeration over here, where I can have some options, okay? And then the xNotifyWait also is a little bit more complicated to the previous one. Before, we just said xNotifyWait. Oh, actually, it's the same. Okay, so never mind. All right, so let's have a look and see what actually happens when we actually run this as is. So we expect it to basically pass in. Okay, so it received 2, 1, 2, 4, 1, 2, 4, and that's because I'm passing in 1, 2, 4. Okay. Now this is basically ESET value with overwrite. In other words, what's going to happen is every single time I call this, it's going to give me a new message inside there. There are a couple of different options, right? If we actually have a look at the definition of this. So this is essentially what that looks like. Let's go to this guy here. All right, so we've got some options over here. I'll just show you what these are. We're using this one, ESET value with overwrite. We've also got ESET bits. Right, let's try that one. Bless you. So, if you guys are you guys familiar with binary? Are you happy with this thing? 1, 2, 4. It's just moving one bit along. Yeah, so it's essentially just one. Now we see 1, 3, 7, and now it remains at 7. So this is a particularly interesting one.
Oh.
So what is actually happening over here is it's not resetting it. Okay, so in other words, every single time it calls it, it basically says, I called that command, I'm going to retain the fact that I actually recalled that command. Okay, useful in certain circumstances where you want to actually keep that particular state.
So you can use that as like a bit flag.
Oh yeah,
bitwise flag.
that's right. But what's also very interesting is that I can also say, all right, look, when you come in here, right, what I want you to do is, if you have a look at these parameters, right, when you come in here, I want you to clear a certain bit. Okay, so let's say, for example, I wanted to clear, let's say, the second bit. Oh, I didn't save it.
Oh, okay.
And we'll have a look at an example as to where this becomes useful in a moment. Alright, so it received 1, 3, and then it's 5, and it remains 5 because it keeps on clearing that too. Okay, so if I wanted to always clear it, I could basically say this, what I'm going to write over here, 0x 1, 2, 3, 4, 5, 6. Okay, this over here is going to be the same as using the previous flag. So if I save this, so now it's going to basically clear it each time, and you'll see that the output is going to be very similar to what we looked at before. 1, 2, 4. Okay, So depending on what you're trying to do. Okay. All right, next one. This is something which, yeah. Okay, so that's that. All right. So that's all the task groups. Now, so you know, when we looked in that task, we have this capability of just sending through a little command. Okay. I can show you a little bit of code that I wrote a little bit earlier this week, where I was actually using this guy on an MQTT broker to basically say, look, get me something, and then go ahead and, depending on what you got, I can basically set up a command, and then I can set up a switch statement after that, and then I can act accordingly. Okay. So communication from one task to another, but the thing is that, you know, we can sort of crook it to basically pass in a pointer or a string, or a pointer to a reference in memory or something like that. But that's not really why it's built. If we want to actually send through sort of packets of data or large packets of data, then we can do something like a queue. We haven't actually done the. Okay, we'll do the queue or the event groups last. So the queue is actually a really straightforward little guy. Okay, let's just go ahead and run this guy, and you'll see that it's actually very easy. So the hard bit is all done, by the way. No more sort of. You don't have to frown so much. It's all good.
Is it static or dynamic?
What?
The queue, the memory usage.
It's. I'm assuming it's static. No. Wouldn't be, because it's essentially done on runtime. So it probably malloc it.
Do you need to specify a maximum size? Or
yes.
You do?
Yeah.
Okay. Maybe
so they're probably using malloc behind the scenes.
Okay.
They're probably just putting it onto the heap.
Okay.
Let's have a look and see how the queue works. Okay. So the queue, we start off by actually creating the queue handler. Okay. Once we've actually created the queue, then we can essentially create the queue by saying xQcreate, and that takes in two parameters. All right, the first parameter is essentially the length of the queue. You can have 1, 2, 10, whatever. And the second parameter is the size of that particular one. So if we wanted to pass in like a string or something like that, it would basically, you know, like depending on the size of it, you could basically say I want a chunk of 10 bytes times 10. You could also basically say I want a pointer in memory, which is basically 4 bytes times how many chunks you want. Okay, so it's possible to just pass in a pointer. Obviously, if you're going to pass in from the local stack, make sure that your current task is not going to run out of scope, because obviously then it'll disappear. Okay, so I've got 2 tasks over here. Okay, they're very straightforward tasks. Okay, the task 1 and task 2. Okay, task 1, listen for HTTP. This one over here. Right, it's got a counter, okay, and then what actually happens is it receives something from HTTP, and then it sends something, okay, and you can see that it's actually just sending a number in this particular case. Why a number? Because I said right at the beginning that you basically want 3 times integers, so 3 ints are allowed on this particular queue, okay, and now, interestingly enough, it also has this thing where it basically says, all right, I'm going to try and push it onto the queue. And it's going to give me that amount of time to be able to push something onto the queue. If that queue is full and it fails to put it onto the queue, it's going to basically go into the second if state, or this else statement over here. Right? Otherwise, if it's okay, it'll basically is able to add it. Now, I've got another task over here, all right, that is just going to wait for something to come onto the queue. And the minute something comes onto the queue, it's going to grab it off the queue and it's going to put it into that particular variable. And then it can actually print that out over here. Everybody tracking?
You don't need to build this?
I've already pre-built everything.
Yeah, okay.
Except for this one. I must have changed the name of it. Okay. So while this is actually cleaning and building, okay, this is going to take a couple of seconds. Maybe I can have a slice of pizza while that's happening. Anybody got any questions?
Is there a dynamically sizing queue? Or is there always just this rule set like 3?
It's not efficient.
Yeah. Any other questions?
Well, you said that the queue likely Malik's data. There's no reason why it couldn't resize the queue.
No, and also there's no reason why you couldn't put a pointer to whatever size you wanted. Yeah. You could have a, I mean, you know, you specify the size of the queue fragments that you push in, but, you know, with the pointer, the sky's the limit. You can put in whatever you want. You can put in the massive structures. You can put in strings. You can put in whatever you want. Blobs. Pointers to MVS. You know, volatile storage. Whatever you like.
I think the data is it's allocated as a contiguous block. Yeah, so you can't just take one and then add another block later. Yeah, unless you copy it to a new area of memory.
Interestingly, they are copied.
Okay.
It's passed in
They
by
are
copy.
copied.
Queues are copied.
Oh, okay.
So when I actually pass something into a queue, it's copied out.
Wait, copy out the handle of the queue or the
No,
queue?
the data.
Oh, okay.
So when I push data into it, it's
Right.
copied into it.
Ah,
Okay.
right.
So that means that even if the original task disappears,
Yeah.
then it's still safe.
Yeah.
It's still sitting on the
It's
queue.
not just getting pointers to the data.
Yeah. Otherwise, you can.
Passed in,
I guess you
it's
can just.
copying the data.
I guess you can just
But if
pass
it's
in
a
a
proper
pointer.
container.
But if you pass in a pointer,
Yeah. You can queue up.
It's the pointer,
yeah,
not what
the pointer will
points
remain there. But if the
Yeah.
original data disappears because it's gone on the scope, then obviously it's
That's
gonna
too
crash.
bad. Soon,
Right.
Soon, almost done.
Almost done. And I get to have 2 slices.
Still have
of pizza.
time for another pizza.
All right. So another 4. So remember I was talking to you earlier on about, I said as you add more files in, that number tends to get a bit bigger. That would mean 24 tends to get larger.
It's a lot of files.
All right. So here we go. So you can see that it's basically added message to a queue, and then it's essentially received message from the queue. Now, if you have a look at this, right, this is popping something onto the stack, and this is reading off the stack, and it's going to allow it to wait for, let's say, it's going to allow it to wait for 5 seconds before it breaks or basically says, I couldn't read anything off the stack. So if I basically come in here and I say this task delay over here is going to be longer than that, then I could expect, right, this thing to start complaining. Let's try and make it break. So now what's going to happen is it's going to have the capability of basically pushing something onto the stack, and it's going to only allow for 1 second. So it's go 1, 2, 3, and then after that it's going to be full, and we can expect that to complain. So doing something with HTTP, this is now waiting for 5 seconds to come out. All right, added message. So let's see if we can get this thing to break. This, by the way, is always, so we should probably put an else statement in here, because this thing is actually complaining every once in a while. We're not actually seeing that. NO.
It's when it times out, right?
Yeah. Because let's just see if we can get that to break. It's a good idea to always try and make something break once in a while. Then you're sure that it's working when it is. Okay, so what I expect to have happen here is it's going to go ahead and put something on the stack. It's going to wait 6 seconds, and then we're going to go, no, it broke. And then essentially, as that 6 seconds expires, it's going to come around in here and going to add something else to the stack. Then it can actually run. And then after it's finished running, it's going to wait another 5 seconds. It's going to, no, it broke. And then it makes sense? Yeah?
Yeah.
They are not quite clear about it.
Oh, okay. All right, so let's see what happens, right? So first thing is I've got 3 buckets. Okay? So I put something in the bucket. Okay? And then what happens is I once I've actually finished putting in the bucket, I wait for 6 seconds. Right, this one over here, right, we'll put something, I'll see you tomorrow, eh? We'll read something off the bucket, but then it's only allowed to wait 5 seconds before it complains. But this delay over here is waiting for 6 seconds. Yeah? So it basically pushes something onto the stack and then waits for 6 seconds. But this thing over here has said I'm only allowed to wait for 5 before I break. And then essentially it'll come over here. Does that make sense? Yeah. Okay. All right, so we can prove that we can break a queue. Great.
Task one's job is to just check the queue, but you just have a very long timeout.
Yeah, that's right. Yeah. So if I make that, let's say, let's make this very short. Let's make this 500. Now what's going to happen next is that essentially this queue is going to get really full very quickly. Yeah? And
You should see the fail to add message.
we should see the fail to add message, but we might need to put a delay in here because this might actually just be able to actually cope with it.
Just cover up the screen.
Yeah, so we'll basically add a delay in here to stop it from being able to consume that queue. Now we'll break it the other way. Now it'll basically try to add things to the queue, and it'll get to the point where it says, no, I can't add anymore. Okay, so still coping.
It's going to take a while, I think.
Yeah. Okay.
Is it?
Well, you get the idea. All right. Hang on.
Maybe you want to decrease the time.
Yeah, I mean, I could decrease that to, let's say, 100 milliseconds. Oh, that's why, because this is 500, not 5,000. That's why it was coping. Okay. Now it should definitely break. Okay, cool.
Oh.
All right, let's have a look at, we'll have a look at events, and then that's it. We're done.
I think the 5,000 is supposed to be on the other task, isn't it?
I've got 5,000 there and 1,000 there. I don't know.
I think it's supposed to be on the other task, but it's okay.
Yeah, it's okay. You guys get that.
That's what live coding's like.
Yeah. All right, last one, and then we're done. Event groups. Okay, so event groups enable me to think of them like an AND clause. I want this to happen, and that for something else to fire. So over here I've got 3 tasks. Okay, so I've got this event group. By the way, this is how I create it. I create an event group, and then I create these bits. Okay, got HTTP and got BLE. The idea is that what I want to do is I want to have something from HTTP, and then I want to have something from BLE. And once I've gotten those two, do I want to actually fire my last task. So the first thing I do is I create this event group, and then I can go ahead and create these tasks. Now what's going to happen is, what's going to happen is, let's just go start with task 1. Task 1 essentially sits there and waits for the event group, and it waits for both bits, and it's got some interesting parameters. Right? What we can actually do is we can actually say we want these bits to clear. Well, if I say true, that basically means that it's got a chance to reset, and now it can basically wait for those bits to actually get set again. If I set that to false, then I can actually have something else fire off it. So I can actually fire to multiple tasks at the same time. Okay. And then over here I can say wait for all bits, and that gives me an opportunity to say, actually I don't care, I just want one of these bits to go off before I actually fire. And then I've got this, you know, the delay again, so I can basically say, yeah, look, wait for this period of time and fail if it doesn't work. All right, so let's have a look at how this looks. So if
you're doing an AND and an OR.
you can do an AND or an OR. So this over here is this is basically just ORing these together to basically give me one final value, and I'm saying I want those both to be. So what I'm saying over here is I want those both to be in place. Wait for all bits. Okay. And also clear on exit, which basically means that when you actually finish running this, when you get past here, those things will then be set back to 0. Okay. In order for me to set that bit, I just say x event group set bits, x event group set bits. I pass in the event, the group event handler, which I created up here. Okay. and then I pass in the bit. Okay, and then I can print something else, and then I can delay. So essentially, this goes ahead and fires. Then some time passes. All right. Actually, I'm going to move this. Actually, we'll just leave it as is. All right.
Those bits are essentially semaphores as well, aren't they?
In a sense, yeah.
Reverse semaphore.
Yeah.
This is a good way to select as well. Another way.
It's you could say that you either want to and all of them, or you want to basically you're going to say either all of them are set or one of them are set, and in that depending on my switches, and then I can fire the task. Okay, so let's have a look at this. idf.py flash monitor. Spelling mistake. Monitor. Right. So this gets blocked. Event group set. Sorry, not that one. This one over here gets blocked. Okay. And we got this thing called got HTTP, got BLE, received HTTP and BLE, and then we essentially can fire. So got HTTP, waits for 2 seconds, and while that's basically waiting, got BLE, got HTTP, wait, get them both, and now we can print that out. So we're ANDing them together in this particular case.
Why is the delay between getting the HTTP and BLE?
Because of this delay over here. You see, I'm not sure if I actually explained this to you. So VTAS delay takes in a parameter, and that's in milliseconds. This is actually in ticks. Okay, so this will wait for a certain amount of ticks to occur. In other words, every single time the CPU crystal basically oscillates, it's going to wait for that. But that's very, 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 very fast. So what we do is we divide that by port tick period. Milliseconds, that gives us milliseconds. So 5,000 is 5 seconds. So this is a delay of 5 seconds. And this is a delay of 2 seconds. Sorry?
Is that by default or your basic?
No, this is the standard convention.
It's platform dependent. That constant is platform dependent. So depending on which microcontroller you're using, the speed is obviously different. But I think the other thing is that port tick period MS. I think that's a RTOS tick. It's not the piece. It's not the microcontroller clock cycle.
No, it is.
Yeah.
It's the standard clock cycle. Yeah.
Really?
Yeah.
Okay.
Am I right?
No, I don't think so.
Maybe I'm wrong.
I saw because if you look inside, I think it says how many hertz is the
Yes, that's right.
RTOS cycle.
So essentially, in the config,
Yeah.
right, you can set the frequency of the chip
That's
to
right.
80 hertz, 80 megahertz or 120 megahertz. But that's what that's operating on. Now,
Yes,
whether or
yes,
not that's
yes.
actually an RTOS tick or a CPU tick, or whether they're actually the same, I'm not sure.
You can look inside if you look at the definition. It's actually tick type 1000 divided by tick rate hertz.
Mm.
Yeah.
So that's the hertz of the chip.
Okay, maybe. I don't know. Okay. I'm not sure.
I'm not
yeah,
sure.
I'm not sure.
Every time you call a function, it's going to do a division.
It's actually sorry.
I think it's macro. I'm not sure.
Yeah.
It's a config FreeRtos hertz.
Yeah.
It's 100. It's defined as 100.
What's
So
the-
it's a FreeRtos hertz. So it's like the RTOS the RTOS ticks. Yeah, it's not a computer tick. Yeah.
Okay. Well, there you go. Sorry? Yeah, they probably would. Yeah.
Yeah.
Yeah. Yeah.
Yeah, but there's like defines. You just have to go down the rabbit hole.
So that brings me to the conclusion of an introduction to FreeRtos. What do you think?
Interesting.
Simpler than I thought it would be.
Oh,
Yeah.
good. That makes me happy.
I didn't follow what you did. I sort of got the gist of it. But
Okay.
I never follow it. People
Ah.
jump up and down.
So I will push this up on my GitHub account,
Awesome.
and I'll clean up the video and also just put that onto YouTube.
If this port tick period NS, is that a constant?
Yeah,
It's 100.
It's actually configurable.
Yeah. You
It's whatever
can
chip
go
you're
into the
running at.
source to configure.
And you can
No,
configure
no,
it.
that's something different. That's what I was going to If your chip's running at 20 megahertz and you put it into a 40 megahertz state,
Then
does
it
the
will
timer
run.
go out?
It will run slower if you do that.
I mean, I can show you where you can configure this.
Yeah, yeah.
It's in the menu
So
maker.
this port tick period MS is a
It's a number.
while time constant.
It's a source file, so you can just write the number 100 or
So
200.
at compile time. So
Yeah.
this 2000 divided by is probably going to end up being a
Whatever it
compile
is.
time expression of the
Yeah.
evaluate. So
Yeah.
it'll be a constant anyway.
Uh-huh.
Yeah.
So there's no division at runtime.
No.
No.
But, this is good. But what happens when your chip changes speed?
That's interesting.
Isn't in the RTOS there's usually a constant which shows you the tick rate per CPU clock. So
Oh, okay, because you were saying that this is the RTOS tick rate.
It's RTOS tick rate, so I
Right.
think it probably needs, there's another layer that actually deals with the change in the
So
CPU
what you're saying
speed.
is that at runtime it will figure out the clock rate, RTOS's clock rate,
Haven't-
with the CPU's
Well, I guess,
yeah, I don't know particularly for FreeRtos, but pretty much every other operating system of this
Yeah.
nature, there's usually something where you can tell what number of ticks there are per number of ticks per second is really what you're after. It's usually like something like 128 or something like that. And it's usually constant you can find.
So if you were to put your CPU into a different
speed.
speed,
Hmm.
it would adjust that accordingly.
Yes. Yeah. The developers thought ahead. They're not going to leave you in a situation where you can't do accurate timing. There'll be a constant. I'll see if I can find it for you.
Okay.
Haven't dealt with a microcontroller that changes speed during runtime though.
Yeah, that would be interesting. I mean, I'm sure you
I-
can.
I
do it,
mean,
but
like,
Doesn't
that's what
ESPs do that? Can't ESPs change speed?
I'm assuming it can.
USBs.
But I've never.
ESPs, sorry,
ESP.
ESPs.
You can change it when you're building it, so you can put in a config, so you can set what kind of clock speed you want to run it. But I don't think you can change it during runtime.
I don't know.
Maybe I don't know. Haven't actually
It's
tried
an
that.
interesting,
Yeah.
interesting idea.
Yeah, because I know in the Arduino IDE you can select the speed you want, but again, like no for ESP32.
ESPs,
Yeah,
it's-
Well, I know that they actually throttle the WROM, this chip over here.
Mhm.
They throttle it because the Wi-Fi can't deal with the speed that it's capable of.
Oh,
So they drop it from 120 megahertz to 80 megahertz, which is still faster than my 486 that I used to.
that's a bummer.
Yeah. All right, cool. So, any questions?
You have a timer feature. So a timer that fire every minute.
Oh, like a timer interrupt.
Like, so what are you trying to do?
Oh, like you just want something. I don't know. If it's a real application, but you just want to fire something for an extended period of time. You don't want to be counting
Yeah.
delays.
So this VTAS delay, all right, is going to sit there idle with an idle task. So,
Oh,
But that's still not firing on the minute.
oh, you can make it fire on the minute. Just so this is 2 seconds. If I say 1,000 times 60, that's
is that a 32-bit
So
integer?
that's firing at 60, 60 seconds into the future.
yeah.
But what if I want it to fire on the minute when the clock reaches?
Oh, you mean in real time clock?
Kind of
Ah, right.
synchronized. So it's not going to be hard real time, but
Yeah. So there.
Yeah.
Using in CPUs.
No.
Yeah. So you can actually there is capability. There is actually a real time clock built in. There's actually several timers. There's 8 timers built into the chip, and there's also the capability of using one of those as a real time clock, and it also has the capability of using a particular protocol. I can't remember its name now. That actually goes over the network and actually sets its time. Yeah. So that's all catered for. That is. I've never really used, but I know that it's there.
Just check. As part of power management, you can enable dynamic frequency changing, so it'll change on the fly between 180, 160, or 240 megahertz. So
Nice.
yeah, you
For
can
ESPs.
power management.
Oh,
So you can turn the power management on, and you get this automatic dynamic frequency scaling. So that's a lot of fun for you.
That's good. Let's go.
Yeah, so
So you can like connect to the wireless, slow it down to what it needs to be, and then after it's finished communicating, speed it up, do processing.
you have to read all the details. But if you're turning that stuff on, you obviously you have a need for around power management. In which case, you know what you're up to. Yes.
We're obviously going to chew your battery life a bit higher.
Yeah.
Cool. All right.
What you were saying in the on the first second of the minutes, you might set your task to have a high priority and a very low delay, and then just check. Like,
Yeah, but I would want to avoid that. A real-time operating system tends to give you that as a feature. And a hard real-time system will give it dead accurate by second examples. Doesn't matter what else.
Yeah. I know that it's supported, but I haven't played with it. But if you have a look at the dockers, there's definitely support for it. I've seen it there. Just a quick one. Just thought that you might find this interesting. All right. I'll just walk through a very quick application with you. It's 2 files. But now that you've actually gone through a lot of the stuff, it should actually make sense to you. So this is just a little sort of demonstration on how to use MQTT. Okay. So over here at the top, I've got some declarations. Don't worry about all that other fluff. I'll get to that in a minute. Over here, you can recognize these two guys. All right, so I've got a queue handler and a task handler. And then when I actually start my application, you can see what I'm doing. I'm basically creating a queue, which has basically got 10 integers in the queue. And then I do something called Wi-Fi init, which I'll get to in a minute. And then I create 2 tasks. And this one has got a task handler, which is now going to be sitting at the top of this file. Now, if I go through to Wi-Fi init, I'll show you what that does. Wi-Fi init, right, basically just initializes Flash, because that's where they keep their Wi-Fi settings in the ESP32. It's not the only place they can keep it there, but by default, that's where it's at. Then I'm going to initialize my TCP adapter. Right. Then I've got this thing called an event loop, which is part of the Wi-Fi stack, which allows me to handle Wi-Fi and TCP connections. And we'll look at that in just a minute. This is actually a callback, which we'll have a look at. Then I do some initialization for my of configuration. I'm setting up my Wi-Fi as a station. Pass in my username and password, and off it goes. Now, this thing over here, what this does, right, is it does this over here. It does this event loop. All right, so over here, every single time something happens with a wireless, this, by the way, is here. So every single time something happens with a wireless, either I'm essentially starting, or I'm connected, or I got an IP address, or I've disconnected, this method or this function is going to fire, and it's going to give me that particular event. So what's happening over here is I've got just some, it's going to start, and then I'm going to say ESP Wi-Fi connect, and then once it's actually connected, I'm going to get an IP address. And now you can see over here, X task notify, right? So that should look familiar to you. That's just notifying a task. All right, so let's go back to my main.c, all right? And let's have a look and see where that's at. So we've got this thing called, I'll just show you this first before we get into that. You've got this thing called generating a reading. This is a very simple little task. And all this is doing is it's essentially generating a random number and pushing it onto a queue and then waiting for 15 seconds. That's all that's doing. Then it starts this other one, unconnected. All right, unconnected looks like this. It basically initializes a whole bunch of fluff, including my MQTT broker, which I'm just using the open sandbox at the moment. And then what it does is it sits here in this infinite loop, and the first thing it does is it just blocks. It just waits. And the first thing that I expect to have happen is this unconnect that we saw just a minute ago. This task notify is going to fire, and it's going to fire with this thing called Wi-Fi connected. Then what's going to happen is it's going to come in here and it's going to say, all right, I've got a command, Wi-Fi connected. Then it's going to initialize MQTT, and it's going to register an event handler for MQTT, and then it's going to start MQTT. When it starts the MQTT, what that's going to do is it's going to call this guy here. And it does the same thing as what you saw on the Wi-Fi. It's just going to sit there in a loop waiting for events to happen. So the first thing that's going to happen is it's going to go ahead and get connected. Okay, and once it's connected, I'm going to notify somebody saying, hey, you've been connected. So that basically comes back into here and it says, hey, you've been connected. Then I'm going to subscribe to a topic and I'm going to publish a topic. And then it breaks and that's it. It's out of here. Then this thing comes in here and it says, all right, something was published. Let's notify that something was published. After it's published, stops, destroys the client, returns. That's it. Done. Now we wait for the next queue to come through. So just having, so you can look at this code, now you can understand what's going on there. No worries. Okay. And, maybe you don't know all the ins and outs or what all the various different things are doing. Yeah, but you can see over here, unconnected, this particular task which we generate over here, all that does is basically wait for a queue, and then once it's got a queue, it basically falls into this switch statement, and that just waits for events to fire and then acts accordingly. So I've got 2 tasks, and I'm able to handle quite complex scenarios of connecting and waiting for IP addresses, and then waiting for just by basically just firing it off like this. So what do you think of that? Very cool. Yeah, and it actually works.
Yeah, that's important.
So much easier than doing MPT on the 8266 libraries are a real mess.
Yeah, that's for sure. And also, like the Arduino libraries do abstract a lot of it out. You don't wind up with these event loops, but if you need fine-grained control, or if you want to do something unconnected or on this, or if you want to handle, if you want to handle very specific scenarios, then this is the way to do it. And you can see it's legible. It's easy to read. It's not like if you spent a half an hour at this, you'd have it no problem. Okay.
When you started a task, you gave it a stack size.
Yes.
How do you decide what stack size you use?
Good question. Okay, so there are a couple of functions. All right, so your first guess is essentially, let me guesstimate it. Okay, it's always going to be that way. And then there's a couple of questions called get watermark. If I recall correctly, I can have a look at this now. If I let's see if I can find something.
So there's a function to get the depth.
It'll tell you. Yeah, it'll tell you what stack size you've got left. Yeah, that's it over here. So this will basically tell you how much stack size you've got left for that particular task. So in the course that I'm doing, I've actually got a whole module on memory management where you can actually have a look at the task, the stack. You can have a look at the stack space. You can have a look at the heap. You can have a look at because also the thing is fragmented and you can't actually malloc a whole bunch of it at once. You've got to basically figure out what the biggest block you've got. So all of these methods are available if you really are concerned about that. But I mean, the ESP32 comes with 512 kilobytes on the stack. But by the time you're actually finished with all the various different bits and pieces which come with it and the reserved stuff, you only actually wind up with, I think it's close to 200. So, but still, that's, if you basically consider that versus, let's say, an Arduino 8 kilobytes, you got ample space to do lots of stuff.
You have 100 tasks and you've given them all.
Yeah, then you got
100 bytes of stack. It adds up pretty quickly.
It does. But then you also, it's for sure. And in that case, you probably might start thinking to yourself, look, I'm either going to start consolidating a lot of that stuff into one task like I showed you before where you can actually just pass in parameters. Or I want to, because one of the other things, of course, you can do is you can destroy these tasks if you don't need them anymore, which will give it back to the stack. Or you can say, I need a bigger microcontroller. Yeah. Cool.
Get a Raspberry Pi.
Yeah, that's right. We'll run Linux. Okay. So, guys, that's it from me. I hope you found that interesting, if not slightly amusing, or just I hope or slightly useful. If so, thumbs up. All right, thank you.
Thanks a lot.
You're welcome. And yeah, I'm going to. What I'll do is I will put this code on GitHub, so you can freely download it at your own leisure. And I'll clean up the video if it worked out okay. No promises. And I'll basically post that on YouTube. There are a couple of little tutorials around with regards to FreeRtos. I tried very hard now to condense pretty much the whole subject into into let's say 1.5 hours, 2 hours, and I think I did okay. And that's pretty much it. There's not very much else to it, actually. You can get into the management and you can get into all the various different blah blah blah. But if you understand the basics, essentially there's two things that you need to think about: tasks and how do I interoperate between tasks. And if you've got that concept, you kind of got FreeRtos. And if you understand why you need it, because doing everything in an event loop can be unscalable, you kind of understand why you'd want to do it. And then, yeah, the sky's the limit from there. Cool. So I'd like to thank you for your attention. It was a pleasure talking to you tonight. And yeah, if you got any questions, reach out to me on either Slack or the meetup. If you guys like the pizza, if you want to, I have paid for it, but if you guys want to basically pass me $1, $2, no bucks, I don't care, doesn't matter. I'll give you my number, and you can just forward that money to me, or you can just give me $5 or whatever. If you don't want to, that's totally fine. I'm happy with that as well. But yeah, I do appreciate you guys coming, and it means a lot to me that you come here and attend and find an interest in it as well. So thank you.
Thank you.
Cool.
Thanks. So, do you have any plans going forward? Like, would you like to run more advanced workshops, or keep a sort of regular sort of session going for people? Or
yeah. So there's been a couple of different ideas, and I'd like to sort of get an idea from you guys. We could do this sort of thing where we do, let's say, for example, take a particular topic and do an in-depth lecture on it. We could also do workshops if you guys are more interested in, like, let's say, getting your hands on in terms of things like setups, or, maybe you're interested in a particular topic and you want to actually, it's easier to explain stuff, and you can definitely cover a lot more ground if you're covering theory or showing code than if you're actually just, everybody's typing it out. But having said that, it's possible to basically take a topic and make sure everybody's mastered by everybody's getting it. So it really depends on what would you guys like? Any ideas, any suggestions? Anything that you're working on that you'd like to sort of get tackled?
I'd like to know what you can do before this Wi-Fi capabilities. First of all, and also Bluetooth. Is it best on Bluetooth?
And the Bluetooth, yeah.
Make some suggestions. There's a. Actually, first ask, is anyone here a member of the space, or are you just here coming along to the ESP32? Sing? Yeah, there's no other members here at the moment? That's okay. Well, Adric, who's quietly hiding at the back there, and myself, who's not hiding quite as effectively as Adric. We're both in the community, been here for a long time. It's great that Mark's come down and do this for everyone. So the space operates in two ways. One is there is membership, basically keeps the space going as people who come down quite regularly. And it doesn't mean you're not welcome because you're not a member. That's not the impression at all. But that's how the space works. People who are just very passionate and they're here and they're using all the equipment around you, the laser codes on. And then we do these things where we want to reach out to people where we're able to help, because for groups like ESP32 or 3D printing stuff, that's really hard for any small group to actually manage this physical space. And so our group is effectively, I feel like, an umbrella for all these other sports groups who couldn't, who wouldn't have the time, I guess, to do that. So we basically want to be self-sustaining, and so some of the other groups are on the fourth Wednesday of the month. There's the ESP32 MicroPython group. So Damien George, the guy who created MicroPython, comes down, and that runs. It's a very powerful group. So even though it's MicroPython, not C, I'm not going to do any turf wars here. Those people know a lot about the ESP32, a lot about peripherals, Wi-Fi, Bluetooth. That's one group. That's you don't have to be a member to come down on the fourth Wednesday of the month. So that's a way to keep in touch. It'd be nice if we can keep an ESP32 IDF group going. Mark Wolf, he and Andrew Nielsen's amazing at mechanical design. If you want to know anything about laser cutters and CNC machines, just come down on Monday night and chat to Andrew. he's done all the mechanical design on a little, almost like a little PlayStation control, but it's all made out of laser cut wood and things like that. Mark Wolf has done the electronics design, so people who can help you with electronics, learning how to make this, and basically that's all coded using the Expressive IDF, and it's all Bluetooth based. So Mark knows that so basically it's built from scratch, an array of buttons and things and joysticks and Bluetooth. So if you want to find out more from people who really know what they're talking about, those guys, and so we're down here pretty much every Saturday. There's a bunch of people from the microcurriculum group, again, myself and others who are very much into MQTT. So basically, if you want to do home automation or things, basically you hook lots of ESP32s together. So we're basically trying to get a gradual build up of ESP32s running services in the space. So one of the first ones that Peter and Kerry put together, it's the sign above the door, which is that red bin means it's Wednesday night. We should put the bins out. And when you put the bins out, the bins appear then outside of the little white hacker space and goes green, and then on Saturday mornings it goes red again to remind us to bring us back in because we're clearly hopeless. But that's I believe it's an ESP32 and that's Bluetooth BLE beacons doing that. So yeah, there's a lot going on. So everyone's welcome to sort of keep coming down and hopefully some people will really get into it and become members. But yeah, so so there's the webpage hacknorm.org, which has a little calendar on the right hand side. There's Twitter, which I think is once again I forgot which one it is. I think it's Hack Melbourne at Hack Melbourne, and there's a Facebook page. So all these are ways of just finding out, and all the meetup pages. And so this space is really just exists for people like us, yourselves, to basically do what you will here. So so don't feel like you need to wait for someone else to organise stuff. If you're keen, please make it happen. The community's here to help you. The community's here to basically say yes, as long as you safe set things on fire. It's all good.
Cool. Thank you for that.
It's an invitation to come down and keep this going. And community and other people will help you out. And there's lots of cool gear here because ESP32s are designed to actually talk to stuff. So so you got laser code, you can make boxes and packaging, design electronics boards, play with all the peripherals, R2C peripherals, SPI peripherals, put OLED displays on. Sion Rosenblum, I think his name. Just Sion. He basically did the Tiny Pico project, which is kind of the world's smallest ESP32 module. It's got really nice peripherals on it. So it was Kickstarter, it was crowdfunded.
Oh, did it start yet?
Well,
I saw it online. I didn't realize
to be strictly honest, Sion just basically did it all on his own recognizance, and he went across to the Shenzhen tour, which is put together by Bella Georgia. But he comes down here every when he can, comes down on the MicroPython nights and so that. So there's a wealth of experience here. Everyone's really nice and sharing. Don't feel like you're only beginning and you can't chat and mix with these people. It's not like that at all. So yeah,
cool.
So a lot of people, little startups or side projects doing cool stuff with ESP32s.
Great. Just in terms of so next month, okay. So yeah, not discounting what you said, absolutely. But when the next ESP32 meetup's coming, just does anybody have any ideas as to? Okay, so firstly, how was the session tonight? Was it too low level? Was it too high level? Was it hitting the right mark? What was your gut feel?
Isn't low level good?
Low level can be good, but it can be overwhelming. So what did you think of it? Was it okay?
I think it's a good mix.
Yeah? Okay, cool. All right, good. So, and everybody sort of...
It's good for me too.
It was good for you?
Yeah.
So, yeah, I mean, it wasn't too complicated. You didn't, oh my God, pointers. Oh. Okay, which is good. All right, cool. So that's great. So next time, would you like to sort of do something similar, or do you want to sort of get your hands on there, and do we want to do a workshop, maybe do a electronic dice? One of the things I've created for the first time was essentially a little sort of LED dice. You got two buttons, you press it, and it basically does a random number, and it comes up with a random dice display, and you can basically toggle one dice off, or you can have two dice, and it sits there juggling until it basically comes to a little number. You can do something like that. So, do we want to do sort of a lab, or do we want to, or is there sort of, as you said, BLE, which is something I'm still trying to get my head around. I've got Bluetooth sorted out, and I can actually communicate to my computer via Bluetooth to the chip, which is kind of cool. We can also do something like that, like a lab like that, just to get something going.
Has everyone got the IDF and stuff going, the ESP32 on top of those? Anyone here who hasn't programmed the ESP32 yet? Cool. Well, maybe that's the thing. It's basically, if anyone who hasn't got started, let's get everyone
Get
you know,
everybody
there we go.
flashing LEDs.
Flashing LEDs. Hello worlds. That's probably a good thing.
Yeah.
Is
Okay.
it? Is everyone? Or is anyone who's sort of at the level tonight basically has basically run a task or pinged a pin out there? Who's basically now compiling firmware onto the ESP32?
Sorry, compiling.
Oh, basically taking some code and flashing like an example. So people
I'm still using the Arduino.
Yeah. Okay.
But I am using an ESP32.
Oh, so you've been using the Arduino IDE.
Yeah.
So you're not. Okay. So who's up and going with the IDF?
ESP IDF.
IDF. Do you want to get going with the IDF?
You do?
Okay, so it sounds like 3 people who need to.
So maybe we can do that next time. We'll basically do a hands-on getting your environment set up. So if you bring your computers, all right, we'll get you sorted out so that you can have what I've got, which is essentially VS Code, IntelliSense, full-blown, compile and flash directly within your environment. And then I can show you this little guy as well. This guy is probably one of the coolest guys out there on the planet, this little guy here. Have you ever seen this before?
What is it?
This is a $10 JTAG, okay?
Ah.
And this allows me to do inline debugging.
Oh.
Do you want to see that?
Yeah.
Yeah?
Maybe next.
You want to see it?
Next
It'll
round.
take me
You
2
mean
minutes.
now?
No? Do you want to see it now?
Yes.
If you can
I
get
can-
it up
okay.
right now. If it's
All
not
right.
too much of an
Just
inconvenience.
start making mistakes.
Yeah, that's hopefully not. All right.
I'm from Perth, so I probably won't be back. But
Oh, okay.
I'm here. I'm developing an energy monitor on ESP32 in MicroPython.
Okay.
So I'm just glad to be in a room with ESP people. Because
Cool.
You know the Slack channel?
Yeah,
There's a
definitely.
Slack channel with lots of, like the MicroPython has a Slack channel,
right.
and ESP32
You're doing the
has a
hack-
Slack
hack-
channel as well.
Hackfig channel or the Slack team or which Slack team? Because there's an ESP32 Slack
Do you
team
JTAG debugger?
as well
Is
as
it actual JTAG?
It's an actual JTAG, yeah.
Oh, it's not called JTAG debugger, but
Oh,
I
there
just
you go. There's 3 of them. There's 3.
Yeah.
what's
Three
the
Slack groups you can join.
the work the
Yeah, I'll have
thing you're using
to
actually communicate with it?
I'll show you.
Because I was using like SP
Do you know the,
link
artifact
and all that sort of
share
stuff.
Oh, no, it's not needed.
Yeah.
I'll show you.
Daniel's
Okay.
Montrose and those guys were-
This will take me 10 seconds to set up, so I'll show you very quickly what I'm doing.
good kind of people. I don't know how strong they are on ESP32, but they certainly do have a very good test.
Yeah.
I'm just going to set this up real fast. Just 1 second.
They always visit. They always pop in here.
Right. Yeah.
Really nice people.
Okay. All right. So I've just set up. So I've got some configurations that I usually set as boilerplate. Okay. What I'm going to do is I'm going to go through to my main function over here. I'm going to go to the side over here where I'm starting the code. This app main over here. I'm just going to put a breakpoint there like that. Very straightforward. Okay. You'll see in a moment. Okay. I'll put another one over there. Okay. All right. So now what I'm going to do is, okay, firstly, I just need to make sure that I'm actually on this directory. So I'll just open this in a terminal. Okay. Now I need to get a command very quickly. Just 1 second. ESP32 course. Let's just go back here. Start a template. Go to the README, which is over here. I'm just going to get the command I need, which is this guy here. Okay, and then go ahead and run that guy. No device found. Oh, I need to plug it in first, otherwise nothing's going to happen. Let me show that to you. So, yeah, so, I mean, this is something that I could probably talk for hours about, but in essence, what you've got is you've got 2 inputs, one going through to your JTAG, which is the little chip over here. Your JTAG then talks to your chip, so you need 2 COM ports. So you'll see a whole bunch of little green lights coming on there. All right, now let's just basically control exit, start that guy. Okay. Alright, that's not going to work right now. We'll basically just... I just need to do something here very quickly. Just 1 sec. I know what's wrong. Actually, what I'm going to do is I'm just going to make sure that I don't have anything else running on these ports. This is going to take me 5 minutes. Just give me a sec. Controls. Okay, so that is failing. Let's just can this, can that, can that, can that. Open in terminal. Okay, that is failing. Good. Let's go to my directory and set the driver. Load all. Okay. Interfaces. Replace driver. One of the biggest problems with these things is the driver on Windows. It keeps on getting replaced by one that it can't use.
Is that because it's got a fake HDR, fake?
Yeah, it's real pain in the ass. Okay, but now that I've done that, I should be able to get this guy started, and it's working. Excellent. So now what I do is I come into debug and go to my main and just open that up a little bit and press play. Sorry? No, you gotta. Yeah, there's. Oh, I've got the wrong file over here. Yes, it is. It's part of the. It's called OpenOCD. The debugger, yeah, it's part of the OpenOCD. Does this make sure I'm in the right place here? Yeah, wait for FreeRtos. Okay, so I've got the wrong file. I just need to get that. I'm just going to go to the build. This isn't seamless, unfortunately. It'd be nice if I could make it seamless, but I haven't quite figured out how to make it completely seamless.
Just while waiting, who's using Windows on their laptop? Mac OS? Yeah, Linux? Okay, so mixture OS was challenging.
Yes.
Yeah, so Visual Studio is only available on Windows, is that right?
VS Code is available everywhere.
No,
So
It's open source.
this is Visual Studio Code. It's
okay.
Electron.
Okay, that's cool. Yeah.
Okay, let's give that a try. Ah. Oh, just save that. Hang on. What am I doing wrong? I got the wrong files open. I'm in a hurry here, so I'm making mistakes.
Oh, yeah.
Okay, close. Close all. There we go. Close all. Let's try this one more time. So I'm going to go in here into launch. That's the wrong file. That's the right file. Control D, 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 / Control S. Try that one more time. Oh, come on. Why is it looking... Oh, I know why. Ah, sorry. That's why. Okay, Control C. I know why. You gotta actually start it. Okay. Because I'm not in the right directory. Start a template. Read me. I'm gonna get it any second now. Just bear with me. I'm sorry it's taking so long.
All right.
Control C. Close that. Paste that. We've got the debugger working. Start this. Yes! Here it goes. All right. And it's coming. Just be patient.
Okay.
The fact that it hasn't aired out means that we're in good shape.
Okay.
Just give it a second. It's coming. The first time it takes a bit of time.
Okay.
And then it sort of kicks in and everything is then fine, and it actually speeds up after that. So yeah, this is going to work. Just give it a second.
Okay.
I hope.
You said this was $10.
This is $10.
AliExpress.
Yeah. And there's different versions. You can get cheaper ones as well. Just stop it and start it again. See if we can actually get it to. I do find that the first time it always is a bit slow, and then after that it works quite well.
What does it actually do?
You'll see. I've got to show you. You can't. You have to experience it.
Is there a software simulation of an ESP?
Unfortunately, no. There isn't. Ah, here it comes, here it comes, here it comes. I just saw the thread stack starting to call, and it. First time, I don't know why, but it does. Yeah. And watch, as I give up, it's probably gonna start.
Do you need to put a breakpoint at in the setup routine because does it work at the declaration?
I mean, it's starting here.
Oh, okay.
Yeah, so that'll be the first line that actually runs.
Right.
Target halted. Why? Oh, I know why. I don't have the right program installed. Oops. Yeah, you've got to have the right application going in there.
Okay.
So let's just adf.py flash monitor. Obviously, it's not going to break on a different application, which is what it's currently running. Let's just actually stop that. Okay, so now it's compiled. Let's just flash it. I haven't tested that actually. Don't see why not.
I've never understood how that.
Yeah.
Any debugger. Yeah.
There we go! Yay! At last. Jeez, that took forever. Alright, good. So now what's happening, right, is I've actually got an inline debugger. So what can actually happen here is I can press, let's say, for example, the step down. Alright, and then, so it's just stepped over. I can go ahead and have a look at, oh, look, I can see my variables in runtime. Okay. Now, what I can do, so if we sort of step over, huh? What is this doing in English?
Yeah.
It's halted the application, and it's actually running on my chip, one line at a time, and I can actually
basically stepping through the program.
Yeah.
And we can look at all the variables.
That's right. And I can step into this function, so I'll press 11, and it'll go straight into that one. Okay, and I can have a look. I can hover over, and I can say, all right, GPI. What is LED1? LED1 is 2. I can come in here, and I can say, all right, let's go ahead and see what is LED1, and it'll basically tell me, oh, it's a variable, which is not very helpful in this particular case. Let's just step out of that. Now this one over here, right, LED params. I can go to my debug console. I can say, all right, what is LED params? It'll basically give me the fact that it's two things. LED is 4 and time is 100. And what I can do is I can also do something like this. LED.time, while this is running, without having to recompile it, is equal to 600. And it's going to actually update that. So I can change values directly in runtime. Okay, so if I come in here and just add that to the watch, all right, you can see now that it's now 600. Okay, so now it'll basically blink a little bit slower than it did before. Now it's just going to hook up there. It's just going to sort of wait there.
Override what the program did with new values.
Yeah.
Or variables.
That's right. And now you can see also like this particular one has been hit, right? So I can put these on the beginning of the tasks, and I can see when the tasks are going to be sort of hit. So
You changed that to 600. Is that because it was on the stack that you could change it?
it doesn't matter. It's just a pointer to reference, so it doesn't matter. It'll be, it's an it knows it's an integer. It'll basically allow me to change it anyway. There's other things I can do, like for
You've got something stored in
Wrong.
ROM or
no, yeah, but you wouldn't.
variables you can't change.
Yeah, constant variables you can't change.
Maybe it's not apparent, but what JTAG is, it's not just something about the ESP32. It actually stands to be around for some, at least decades, on any sort of advanced microprocessor, because I've heard people realize what these things are getting too complex and to basically test, and so they basically put a standard interface. It basically allows it to just a standard interface to the microprocessor, stop the processor and read and write any part of memory effectively. And so when you compile your program, you end up with a memory map, and the program sort of talking to the JTAG interface knows basically, hey, if you when you put a debug statement, say stop at that line, it knows what processor address to stop the program. And when you're talking about variables, be they on the stack, wherever, it just knows what memory location they're at. So it's using that JTAG to really stop the processor, read and write memory. And then the software on your laptop makes it all look like magic.
How does it work with multiple cores?
It's just as part of it's an extended part of standard because you typically have shared memory between the cores, so it's still just reading and writing from shared memory, and you basically just
when the breakpoint hits, does it pause both cores?
Yeah, when it hits that line of code, it'll
pause both. If either processor hits it, they'll stop.
This is very ordinary in most programming languages, but the only reason it's exciting is because it's on an embedded chip. You know, if you're developing for Windows or Mac or phones or whatever, then it's built in. Everyone's got it.
But what's really cool is, specifically for debugging tasks, you can come in here and you can say, edit this breakpoint, and you can say, actually, only break on an expression. Let's say when L time, let's say, for example, is equal to 1000. Okay, now, if you've got, let's say, for example, a piece of code that's, now this is going to be a conditional breakpoint. And why that's good is because if you've got, let's say, for example, a task that's running several hundred times a second or several thousand times a second, you don't want to have to sit, and something crashes. What is going on? Right, now you can essentially go in there and you can say only break at that point, and it'll only basically highlight that point, and you can basically step through, see the variables. So, yeah, it's
yeah,
kind of like that. Yeah, you could kind of think about it like that. Yeah. And for $10, I highly recommend you get one. Setting it up can be a real challenge, but I've kind of got that figured out, so I can help you with that. It's all documented. Sorry? AliExpress. Just get the cheapest one you can find.
So it's any JTAG reader.
Yeah, so this is an FT2232.
That's the serial ESP chip, isn't it?
Isn't
that just a USB to serial converter?
Yeah, you're right.
Yeah.
It's this thing here, so I'll show you in here. Yeah? Just 1 second. It's just open OCD. It's this guy here. It's FT2232. So that's the actual chip that I'm using. Okay. And it's essentially a JTAG chip. So that little chip on there is this guy over here. It comes in different form factors. This is just a breakout board. And the only trouble is it's a little bit tricky to get the drivers working on Windows, but once you actually understand how to do that, you get this capability. And when you're writing applications, and specifically if you've got lots of RTOS tasks talking to each other, and you don't want to wind up with thousands of print statements, sometimes it's just easier. Breakpoint, that's fine. Oh yeah, that's where I'm clobbering memory. Oh yeah, that's where I've got a wild pointer. Oh yeah, this is where, it makes it really easy to see what's going on.
Just out of interest, could you show me the rest of the cool stuff?
Yeah. Yeah. So you can see what's actually being called over here. So it'll take you through what the process flow was. Now, just out of interest sakes, right? Have you ever heard of Segar? You can see the various different threads. So it'll actually show you what thread you're on as well. So if you've got multiple threads, which you'll have two of, you'll have a different ID, and it'll tell you what hit it, which thread hit it. Okay. What's really cool is that you can actually configure this guy to give you an output dump. Okay, and then from there, you can basically plug that output into something called Segar. That'll give you. And this is something I've just started to sort of look at. It'll give you a graphical interface I think it's this guy here. No. Sorry, 1 second. This. It'll give you a graphical interface, a free application that you can download. You plug that in here, and what it'll do is it'll give you this guy, where it'll actually tell you all the various different tasks and when they're fired, and you can actually see, you actually get a full process map as to how this thing actually looks and works. So you can actually see, oh yeah, it was running on this task and then it ran on that task for that many milliseconds and it ran on this, and you can basically zoom in and out and what have you.
Nice.
No, that's after the fact. So yeah, so you get a dump from the JTAG. You can basically configure it to do that, and then you can plug it in, and it'll give you, and then you can optimize it or find bugs and stuff like that.
These conditions. And
Yeah. Sorry.
Is this thing aware of what an ESP32 is?
No. So what happens is it's generic enough. So yeah. So what happens is you go into the IDF config, and you tell it that that you want to basically dump a file, and when you plug in the JTAG, it's talking to a service on your on your machine, and what will happen is that will actually create a file. Then you plug that dump into this application, and it'll tell you what happened. So yeah, there you go. So extra bonus for the evening.
Thank you.
Yeah, cool. Yeah.
What was that website?
FreeRtos. Yeah, and this particular tool is called Sega.org.
I've posted in the Slack.
Uh-huh.
I've posted a link in the
Okay,
Slack.
cool.
So, yeah.
All right. What's the time?
It's
What did you think?
9:30.
I enjoyed it.
Yeah. Cool.
I'm going to start using FreeRtos. I had a look. You can't get it from Raspberry Pi, can you?
FreeRtos.
I don't think so.
Oh, that's something I forgot to mention actually. That was a good question. Sorry for cutting you off there. Just if you're wondering about sort of this, I'll just show you this quickly. All right. So if you have a look at FreeRtos, the line down over here, right? It's essentially supported. FreeRtos as a system is supported for all of these chips. The Texas Instruments, the ARM, the RISC-V, the PIC microchip. Right, so all of these things actually use ARM. Oh, sorry, FreeRtos. It's in millions of devices, and chances are you probably interacted with it to some time today.
And Amazon have a flavor of.
That's correct. Yes.
Run Lambda functions and all.
That's right, and you can actually dump that into your chip as well. So you can actually get FreeRtos, an AWS FreeRtos or the Amazon FreeRtos embedded in your chip, and then you'll be able to use things like you'll be able to run Lambda functions directly from the ESP32, and it gets wild.
Topic for another presentation.
Yeah. I haven't looked at that, but I mean the whole AWS ecosystem is pretty overwhelming.
Yeah.
I don't think you can get it from Raspberry Pi though. A year ago I looked and I don't think you could.
AWS one?
The FreeRtos?
Yeah,
FreeRtos? You could probably run it within the Linux kernel itself. So essentially it's 3 files, there's C files, you can compile them into GCC. So, you could probably, because...
Yeah, I think some people try to do that, but it's a problem.
Oh, really?
I don't know why.
Well, maybe worthwhile looking at. I know that you can run FreeRtos on a Linux system.
Another question, a real-time operating system normally, or a hard one would be, you guarantee certain reaction times. But none of what you were doing was like that, so this is like a soft data.
Yes. Yeah.
How big's the code?
It's a couple of kilobytes. It's tiny. I think, from what I recall, right, I think the actual FreeRtos, when it's actually running in memory, it's using 200 bytes. It's tiny. And I think that the entire code is about, I think it's in Flash. I stand to be corrected. I can't remember if it was 20 kilobytes or 200 kilobytes. It's 20 kilobytes. I don't remember.
So you could run it on a tiny ADR?
No, I don't think you can. You need a 32-bit system. I don't think it'll work on an 8-bit system. And You do need, look, I mean, for simple AVRs and stuff like that, the event loop's going to work. You know, you don't need anything more complicated than that. It's just, when you want to scale stuff, then FreeRtos really comes to help. Yeah. Oh, they got their point. I mean, there's a new chip that I'm really, really interested in, the Paduk. Have you guys heard of it? Okay, it's an 8-bit microcontroller. Okay, the thing about this particular 8-bit microcontroller, it's about to go open source. So we're about to be able to sort of create programmers, and it has built-in debuggers, and it basically is going to be open source and what have you. Right? It's a tiny little microchip. It's got like no memory. It's got like 4 pins, whatever. But what makes this thing so appealing is it costs 3 cents. It's 3 cents. Yeah, but that costs much more. It's like 50 cents. This thing, 3 cents. You can buy, the shipping is going to cost you more than the actual chip. Yeah.
What's it called?
The Paduk. The P-A-D-U-K. So there's a guy, have you ever heard of EEV blog?
Yeah.
He's a guy, Scott, he's basically doing this whole initiative with the Paduk. You know, if you have a look on his YouTube channel, you look for the cheapest microcontroller. He's got like 2 hours of content in there, and he's actually reverse engineered it, and now he's actually coming out with a program that is going to basically just say, everybody go ahead and be merry, and you know, you have to spend like $3 for shipping, but then you basically spend $10 buying like 3,000 of these chips, literally. Sorry? Yeah, seriously. You know, so and apparently you can also get services that can pre-program them. So you know, you buy them, and if you got if you're trying to drive thousands of LEDs, it might be a great solution for that. So, yeah. Anyway, it's pretty exciting. All right. So, guys, anything else you'd like to know, or?
Your phone number.
Yeah, there you go. We've spoken to each other before, haven't we?
That's right.
If from tomorrow you start getting lots of calls trying to sell you life insurance.
No, then we know why. Cool. Guys, thank you for your attendance, and thank you. I hope you guys found it interesting or enjoyable.
Sorry?
Yeah.
Oh, yeah.
Good. I'm glad you liked it. Yeah. I want to stop this guy. Oh, there we go.